Hey class, welcome back. Today we wanted to continue our look at the different categories of materials as far as how electromagnetic waves interact with materials. So last time we looked at conduction and dielectrics, which are more related to the electric field. So now we're going to look at magnetic materials, which of course deal more with magnetic fields. Quick historical background first. The individual we're looking at today was educated at the University of Erlangen, I guess. He worked at the University of Munich. Here's a picture of this gentleman. Maybe you recognize him. This is George Simon Ohm. So what are some notable things? Probably the most notable is he published the galvanic circuit investigated mathematically in 1827, which is where he introduced for the first time Ohm's law, for which is named after him. In this book, he also introduced the concept of the electromotive force, and he also had numerous other writings. Incidentally, the book was not initially well received, but eventually recognized by the Royal Society in 1841 with a Copley Medal. So hopefully we're all familiar with this, that he is honored with his name ohm being the SI unit for resistance or impedance. So again, we're continuing on with part 5, wave propagation in materials. Again, like I said, we talked about conductors and dielectrics last time, so we're going to look at the third classification of materials as far as electromagnetic waves are concerned, which is magnetic materials. So the most important characteristic, at least as far as this class of materials is concerned, is that of magnetization. Magnetization is the phenomenon by means of which the orbital and spin motions of electrons are influenced by some external magnetic field or force. So when an electron orbits a nucleus, if you think about it in a sense, this is equivalent to a current loop, that is moving charge. So this is analogous then to an electric dipole. So in these types of materials, this gives rise to a magnetic dipole as seen below. So if we have this nucleus and have the direction in and out of the sheet, we have this charge traveling around it. Well, this is, of course, is a current loop. So according to Maxwell's equations, we should have some corresponding magnetic response to that. So the strength of the dipole then of this molecule is defined by the magnetic dipole moment, or lowercase m. So this is given by this equation here, where we've got the area, and we have the current, and then we have that direction vector. So this is just on the molecular level. So in many materials, the net magnetic moment of each atom is 0 on average. An external magnetic field has the effect of inducing a net dipole moment, therefore magnetizing the material. So they start to make these things line up. So this type of magnetization is known as diamagnetism, and is prevalent in pretty much all materials to some degree or another. Now, granted, there are many materials that it's almost 0, but then there are others that when you get it near a magnet, it will magnetize the material. There are other materials where the individual atoms possess a net non-zero magnetic moment, even in the absence of an external magnetic field. So these permanent magnetic moments of the individual atoms are, however, randomly oriented. That is, they aren't all in the same direction. So that net magnetization on a macroscopic scale is 0. So if you have a lump of the material, it would not appear to be magnetic, whereas there is some magnetization going on the molecular level. So an applied magnetic field has the effect of exerting torques on the individual permanent dipoles on a macroscopic scale. This causes alignment into a partially coherent way along the magnetic field, that is normal with the normal to the current loop directed along the magnetic field. This phenomena in certain materials is known as paramagnetism. There are yet other materials known as ferromagnetic, antiferromagnetic, and ferrimagnetic materials that exhibit permanent macro-level magnetization even in the absence of an applied field. For ferromagnetic, these are materials such as iron, as the primary one. They contain unpaired electrons, each with a small magnetic field of its own, that align readily with each other in response to an external magnetic field. This alignment tends to persist even after the magnetic field is removed, and this is a phenomenon that we refer to as hysteresis. We'll look at that in a little more detail in just a second. The next is antiferromagnetic. The magnetic moments of atoms or molecules, usually related to the spin of the electrons, align in a regular pattern with neighboring spins. These, of course, these are on different sublattices pointing in opposite directions. Finally, we've got ferri, as opposed to ferromagnetic. The magnetic moments of some neighboring atoms point in opposite directions, with a net magnetization still resulting because of differences in magnitude of the opposite moments. So while they do cancel out some, they don't cancel out totally. So I don't want to, it's a little bit beyond the scope of this course to drill down into these. I just wanted you to be familiar with some of the different types of magnetic materials. There's other courses that deal with this in detail if you're interested. We're just going to look more on the general case of Maxwell's equations and how it applies to these magnetic fields when they are present. So now we're going to look on a macroscopic scale, that is on the bigger scale. We looked at the molecular level. We're going to back out now and look at the material as a whole. We can now define a new vector, capital M, called the magnetization vector. So this is the magnetic dipole moment per unit volume. So before we were looking at the magnetic dipole on the molecule, now we're looking per unit volume. So if we have some number of molecules, we'll call it capital N per unit volume, and this is a differential volume, delta V. We can express this mathematically with this formula here, where we take the molecular dipole moments and we sum those up over this volume, which goes from 1 to the number of molecules. So that basically just results in the number of molecules times the moments. And of course, this is a vector, so they can cancel each other out. There can be some form if they're not lined up in the same direction, so just be aware of that. Again, where M is the average dipole moment per molecule. So this new vector is related then to our magnetic field, capital B, which really is our flux density in the material, by this equation here. So now we have our magnetic vector is equal to this equation, which involves our magnetic flux density vector. So we're introducing this new term here, chi sub m. So this is known as the magnetic susceptibility. And this is just something we measure, right, for each type of material. And it measures the ability of a material to become magnetized. So more magnetic materials will have a larger number, smaller ones not so much. So if we return to our infinite plane example, where we have our infinite current sheet that's creating this propagating electromagnetic wave, with the modification now that just on each side of the plane we now have a magnetic material with the susceptibility of chi sub m. We now need to take into account this induced magnetic field, and it should entirely be in the y direction and uniform in x and y. Thus the induced dipoles are all oriented with their axes in the y direction, such that on a macroscopic scale we now have this definition. This is for our special case definition of our magnetic field. So it's all in the y direction, just as we said. So if we now consider an infinitesimal surface, delta y, delta z, that's parallel to the xz plane, the dipole moments line up with the magnetic field and form apparent current loops referred to as magnetization current in the plane as seen on the next slide. So this is very similar to what we talked about in dielectric materials, whereas we have the electrons can be moving back and forth even though they don't actually leave the molecule themselves as we do have when we have real current flow. They just bounce back and forth. Same kind of things going on here. So again, this still is moving charge, and so because it's still a moving charge, even though it's a little different than what we're used to, this is still a form of current flow that we have to account for now. So if we look at the diagram here, you see on each molecule they start to line up. So as we start to take this delta Z distance here to create this volume, now it starts to look like, if you add all these up, a net current flow. So this apparent magnetic current can now be used to formulate a magnetic current density, which can be shown to be defined as magnetic current density. It's equal to the curl of the magnetic vector, so del crossed M. Well, that being the case, Maxwell's equations say that all current flow has to be accounted for, so we need to account for this in our original form of Ampere's law. We'll do it in differential form as follows. So we have the curl of H, but we can replace H with this constitutive relationship. Remember that H is equal to, or the magnetic field vector is equal to the flux density vector divided by our permittivity in free space. And so this will be equal to normal current flow plus this new apparent current flow due to the magnetization of the medium. And again, that's then plus just the time derivative of our displacement current, which has always been there in Ampere's law. Well, we can do some finagling now. So we know that we can, this magnetic current density is defined as the curl of the magnetization vector. So we can substitute that in, and then we can do some rearranging. And so this gets us really close back to our original form of Ampere's law, where the right-hand side is what we've seen before when we originally derived it. On the left-hand side, it used to be the curl of the magnetic field, or the curl of H. Well, now we have this in place of it. So this implies then that H is equal to our flux density divided by the permeability minus our magnetization vector. So let's see if it kind of makes sense, right? So if we have this external magnetic field producing this flux density, and then we have some magnetization already present in the material, the resultant magnetic intensity would be the difference in the two. So substituting this definition for M back in, we will get this equation here. So this is what we said M was defined as when we introduced this susceptibility, magnetic susceptibility, into this equation. Well, we can combine like terms here and come up with that this is now just the flux density over the permeability times 1 plus the susceptibility. Well, we're going to introduce a new term here, this mu sub r, which we're going to just arbitrarily say is 1 plus chi-m, or 1 plus the magnetization susceptibility. And we're going to define just a overall permeability as the permeability of free space times this new mu sub r, which we're going to call the relative permeability. So now we just refer to mu as the permeability, and that's due to the material. So we have to account for that by this relative permeability if we're dealing with some magnetic material. If there is no magnetic material, this chi sub m is 0, which makes this all equal to 1. So that's why we come up with mu sub 0 for free space permeability. So if we're dealing with anisotropic magnetic material, which is not uncommon, the permeability can vary depending upon direction. So this being the case, much like we saw with dielectrics, the relationship between the magnetic intensity vector and the magnetic flux vector can be expressed in tensor form. So here, this is going to account for, am I moving in the x direction, the y direction, some direction in between. This tensor will take care of that if the permeability changes depend on direction. So there are cases in which the relationship between the flux density and the magnetic field intensity for some types of materials has a nonlinear relationship. Well, this results then in a non-unique value for the relative permeability for that given material. The result of this then is what we call a hysteresis relationship. And the best way to describe that is to look at it on a graph. So let's look at that. So on this graph, we're going to note that the horizontal axis is our magnetic field intensity, and our vertical axis is our flux density vector. And so we're starting with this material at rest at A. And so we start to induce a magnetic field in the vicinity of this material. And as we do, our flux density and our magnetic field intensity in the material, our medium, starts to increase along this line until we get to B, which is the maximum that it'll be for this material. So that's all fine and good. But now as we start to decrease the magnetic field in the presence of this material, of course, the flux density and the magnetic field intensity will start to decline. Well, when it does, it doesn't go back along the same path that it did before, because the permeability is dependent on direction here. So it actually goes along this line here. So as we come all the way back to where the magnetic field intensity H is 0, we still have some flux density apparent in the material, and it'll continue to go down until it reverses the magnetic field intensity magnitude, and then it'll go down to this new point E. So then if we start to put a magnetic field on it again, then it would come along this path going back towards the B. So you can see here that your position in time here depends on what happened before and what direction you were coming from. So this is another example of one of those types of loops, a hysteresis loop. And so again, this would be the initial magnetization curve. And so it'll come up here, and then as we start to decrease the magnetic field in the area, then it starts to come along this path. And you can see that at these 0 points, they're not both 0 as when they were started, B and H. And so you have to follow these crazy loops. So the crazy thing is on the next slide. So for here, what could happen is, we have this initial curve coming up this way. And as we start to decrease the field, you can come along this path and we start to increase it again. Well, if we were to go along this curve here, let's say we don't keep the field on until we get all the way maximum. Let's say we stop it here and then start to decrease it. You can see there's even yet another curve that we follow. And so crazy things can happen in these types of materials as you start varying the magnetic field. And so one practical place that we see this many times is in transformers. So if you deal with transformers in a building, they usually have an iron core. So as loads start to increase and decrease, whether they're in the daytime and then in the nighttime, you'll start to see the coil, the magnetization inside the coil follow one of these hysteresis curves. So it can vary greatly by material. So you can have what we call soft materials and hard materials. And so again, if you start from the 0 on the soft material, it'll go up pretty fast and it has a much steeper curve. Whereas if you go to a hard material, it's going to take a while to come over here to get that fully magnetized. And then when you do start to pull it back, the flux density is going to taper off much slower until you get to a certain point. And so, just be aware, depending on what type of material you're dealing with, your hysteresis loops can vary greatly.